I'm really tickled to be here talking to you this morning. I want to make sure you're not going to be disappointed or anything by what I'm going to try and cover, though. I have in the past at LCA given talks about, sort of deep details of software-defined radio and how to do everything from an A to D and a D to A converter and sort of first principles. But what I want to talk about today is something a little bit different. As most of you who've ever been to an LCA before or have heard me give a talk somewhere else probably know, I like playing around with high-powered model rockets. Out of curiosity, how many of you have not ever heard me give a talk somewhere before? Wow, fresh meat, I love it, awesome. Okay, so I like to play with high-power model rockets, and I have managed to encourage a number of my friends, both here and in other places, to join me in this hobby. We love playing around. Just to give you a sense of scale, that airframe is about 102 millimeters in diameter and a little over 2 meters long, and was on the way to about Mach 1.3, and that one would have been 4.5 kilometers above ground. I think that's about right. It would have been a whole lot more exciting if I'd gotten anything other than the red bits back, but that's a story for another day. But it's sort of a relevant story because the fact that that was an airframe I had put a lot of time and energy into and was using to try and get my level 3 high power certification, and I ended up being the victim of a bug in the firmware of a commercial flight computer board. Proprietary commercial board. Has a lot to do with why for the last few years I've been involved in doing open source hardware and software for avionics for high-powered rockets. And so what I really want to do this morning is show you sort of the progression that got us from Bdale thinks it'd be cool to do some open source avionics for high-powered model rockets to how we picked the radio chip that we're using for the telemetry stuff and some of the decisions we made along the way. And I'll throw in a few sort of hints and kinks about the designs that we've ended up using and what it's taken to make these various boards work well. And so this is really sort of focused on the radio hardware part of the experience we've had. And then Keith's going to follow me, and he'll be talking about the modulation and coding schemes that we're using on the radio links and the immense amount of fun he's had learning how to replace things that some of our hardware provided in hardware that later generations didn't. So I guess before I go any further, can everybody hear me okay? It's all right? You can't. Do you want to move somewhere, or do I need to do something different? I think is the mic actually doing its thing? Yes. So it's okay for you guys back there. All right. I don't know if it's just where you're sitting or what, but if you want to get up and move, I won't be offended by the motion at all. Okay, I just want to make sure everybody's good. Okay, so why do we want radios and rockets to start with? Well, the whole point of flying with the kinds of flight computers that Keith and I work on is that we'd like to be able to recover the airframe for post-flight data analysis and for reuse. These are not like, fireworks rockets. These are rockets that they're more like sounding rockets. They're things that we're trying to do stuff with, and we want to get them back and be able to fly them again. So the most important thing we do these days with the radio is we get GPS position updates from a GPS receiver in the airframe to tell us where the airframe is through the entire flight. And so that after it's come back to the ground, we know where to go find it. And then sometimes, depending on the topography of where the airframe lands, we still sometimes end up using traditional radio direction finding techniques, going out with directional antennas and where's the signal the strongest from. And in Colorado, this often happens because there are small canyons adjacent to some of our launch sites. And on a bad day, you end up down in the canyon, and you got to figure out which little branch of the canyon the airframe's up in. In eastern Oregon, it's all about which sagebrush the rabbits pulled your airframe under to hide it. And then when things go wrong, as in you don't have a nominal deployment sequence of the parachutes, and the airframe comes back in hot and slams the ground at ridiculous speed, the data that's been recorded by receivers on the ground may be all that you get. And there have been a couple of times where the primary mission objective might still have been met. If what you're trying to do is understand if a new motor propellant formulation really worked right, and you got to watch and video a beautiful burn, and you got enough accelerometer data from the airframe in flight to be able to confirm that yes, that motor performed nominally, the fact that the recovery system failed to deploy and the airframe came back in tatters might not be your biggest concern. I have friends like that in the hobby. And fortunately, some of them actually hand me their motors to fly sometimes, so that can be real. But it's also really important to be able to figure out what went wrong so it doesn't happen again. So when I first started designing flight computer stuff, the idea was to sort of take this a piece at a time. I had this sort of sense that the right answer would be a modular approach, so I started designing a flight computer, which I gave an extensive talk about at LCA in 2008. That would have been Melbourne, I think? Don't remember. So there's no onboard radio or GPS, but there were 2 serial ports available. And the idea that I had was one of those would be used for GPS and one for radio. And of course, SparkFun sold some little GPS modules with serial interfaces, so that part wasn't hard. And this is what that board looked like. Some of you may remember these photos, some of you this will be new for. That was the top of the board. This was done in 2 layers, really cheap circuit board fab. A hand-loaded surface mount with frickin' huge parts by my modern standards. These are 1206 passives and things you can actually, see and work with without microscopes. This is the back of the board with an LPC. What the heck was it? That was it was an NXP ARM7 device, and that was a pretty cool board. But in all honesty, it never flew. And the reason it never flew is that it took me a while to get development tools together, to get software written for it. I was at the point where I was getting close to flying it. And Keith and I ended up sitting next to each other at a conference where we were scratching our heads about what do you do about a radio? Because while I was developing that board, in parallel with that, I had gone and pursued my level 3 high power certification project. And because the guy who was mentoring me through that process was uncomfortable with the idea of my flying my own electronics to control the rocket, since he didn't know me that well and certainly didn't know my electronics at all. He had convinced me to instead fly some commercial altimeter boards to do the parachute deployment. And that was all fine, except as I said, there ended up being a bug in one of them and it didn't go so well. But in the process, we became aware of the fact that it would have been really good to have had telemetry from that flight. It would have been really good to have had radio direction finding from all of the pieces of that project. And so I really wanted to put a radio in before I actually went and flew the thing. The problem is, most of the license-free radios out there just don't have the kind of range we want, or at least at that time they didn't. Things have gotten better, but when you go look at, sort of XB space, those things were just barely in existence when I was starting to play with this, and the early units didn't have anything like the kind of range we wanted, and they were operating on frequency bands that were harder to get ground side antennas and receiving equipment for and so forth. So I really wasn't totally satisfied with that. Ham radio transceivers, even HTs, are fairly large and clunky and heavy, and trying to figure out how to interface to one of those in the rocket environment wasn't terribly exciting. We're fundamentally looking for something that was a data radio. So I had basically come to the conclusion that the right answer was going to be to design a radio board. There's a company in the US called Big Red Bee, run by a mutual friend of ours, that makes some really cool products. One of them that Keith and I both had was called a Beeline, and it was a very cute little circuit board that had a PIC and a TI ChipCon transmitter called the CC1050 on it. The 1050 is a digital transmitter that's meant for use in things like, garage door opening systems or something like this. It supports a modest number of modulation schemes, and in any case, in this particular application, it had been programmed to put out FM audio beeps. So if you had an FM, a 2 meter, 70 centimeter, in this case 70 centimeter HT with a little Yagi, you could use this for radio direction finding. It would occasionally put out the call sign to meet amateur radio regulatory requirements. But it wasn't very hackable as it was built. And what I mean by that is there were extra pins on the PIC that you could have used to provide some serial data in from the flight computer, but they weren't brought out to anything that you could easily attach to. And the version of the PIC he'd chosen, an earlier version of the firmware, the source code was actually up on his site. I pulled it down, I studied it. It made complete sense to me, but he was using almost all of the memory space in the PIC, and there wasn't really any room yet left for processing a serial data stream. But it was kind of a promising idea. So I said, I went and looked up the parts, and the CC1050 was pretty cheap and easily available. And I said, so let's just build a variation of the B line that has a better processor with a little more memory so we can hack on it, maybe a real serial port, you know, like a bigger PIC. And I was actually in the middle. Keith and I had talked about it, and it's like, yeah, that would probably make sense. So I was in the process of designing that board while sitting in the back of sessions at a conference in California, when a good friend of mine, Mike K3MC, walked up and threw this little board in my lap and said, hey, Bdale, look at this. And it was a cute little board with a single little piece of silicon in the middle of it and a bunch of passive components. And I said, oh, what's this? And he said, it's an RF system on chip. And it turns out what he was showing us was the then very new TI ChipCon CC1111. And that part for us ended up being sort of a revelation. Here was a part that was available in the US from places like DigiKey for $7 a piece, quantity 1. It's an 8051 microcontroller with 32K of flash and 4K of RAM, and you know, a really well-designed digital radio transceiver and a bunch of other I/O stuff all on one chip. And we realized all of a sudden that, you know, it wasn't an ARM. It wouldn't be as much fun to write code for, and in a lot of ways, I'd kind of have to throw everything out and start over again. But with that part, we really could do the whole flight computer with the radio stuff all sort of integrated into one board. Wouldn't that be cool? And you know, the parts cost would actually be less than just building the radio board. So there was born this thing called Telemetrum version 0.1. As I said, it was sort of built around this TI ChipCon CC1111F32. We've used that part a lot. It's still available. It still works great. It's shown up in other places. There have been toys made using this. There have been other sorts of devices. A couple of things that were sort of magical to us. It had built-in USB. That's the difference between the 1110 and the 1111, is the 1111 had built-in USB. And frankly, I had already at that point in history grown completely tired of dealing with development boards that had, you know, some pins on the edge of the board, and you had to have the adapter to get to the serial port or the adapter to get to the USB or something. The whole Arduino world's fascination with FTDI interface cables and stuff just didn't make sense to me. And so the fact that it had USB was a really big deal. So, you know, we added some baro and acceleration sensors, some additional flash for data storage, a couple of FET circuits for firing pyro charges, and some LiPo battery support. By the way, the LiPo battery support I hadn't even thought about until I gave the talk on my original board design at LCA. And I don't remember who it was in the audience, but somebody in the Q&A session stuck their hand up and said, have you thought about using lithium polymer batteries? And so I sort of owe my intrigue with LiPos to that session. And then there was a spare serial port available on the chip, which we used for we're going to use for attaching a separate GPS module. So at that point, we still weren't thinking of GPS on the board. And I ended up picking the 70 centimeter ham band around 435 megahertz. And the big reason for this in the US is that unlike here in Australia, where you have a apparently slightly more enlightened, at least some of the time, communications authority, in the US there's really no usable, unlicensed spectrum that an average citizen can play with without going through a device-type certification process. The Part 15 regulations are, in other words, kind of onerous. They're meant to enable the vast majority of citizens to be able to buy radio-enabled products, but the expectation is that those radio-enabled products are designed by consummate professionals and put through a certification process to ensure that those poor citizens couldn't possibly accidentally have something go wrong. And the consequence of that is that Part 15 certification costs an average of $15,000 per product cycle. And that's kind of a pain. And then to meet our original performance goal of reliable data on any flight at Northern Colorado Rocketry's North Site, which has a altitude waiver, standing waiver to 20,000 feet above ground with windows available to 35,000, and taken advantage of a bunch of the capabilities that were in the CC1111's digital radio, we ended up choosing to use 38K4 Gaussian frequency shift keying with a forward error correction on it. That's a rate 1/2 constraint 4 convolutional code. If you don't understand what that means, hang around, because Keith is going to explain a whole lot more about it in excruciating detail than you really want to know. But this is the cool picture. That was the board. Minus one really annoying part, which these two holes were for the leads of a 1,000 microfarad electrolytic cap to be used in the pyro firing circuit. And that part ended up being a little bit of a hassle, because the mechanics of trying to keep a big-ass electrolytic cap from not moving around when you're hitting something with a lot of acceleration and vibration is kind of interesting. But just to point it out, this is the interesting part. That's the CC1111 right there. And this part over here is the UHF balun and filter assembly to basically take the differential output and input interface on that transceiver chip and bring it out to a single-ended antenna connection at 50 ohms over here. That footprint on the end of the board was designed so that an edge-launched SMA connector could be soldered on. But I really have only ever used those in a couple of odd circumstances and for bench testing. Almost always what we end up doing is soldering a wire whip to that center pin and just letting it stick out into the airframe. So we have a quarter wave whip on the transmitting side. That part, the radio puts out 10 milliwatts or plus 10 dBm. Doesn't sound like very much, does it? I forget what the numbers are that with our current modulation and coding scheme, the theoretical range ought to be on the order of 30 kilometers in free space or something like that. Yeah, so if we're talking about, if you're using like a handheld 5-element Yagi on the ground and a quarter wave whip in the airframe and things are oriented right and you're in free space, i.e., approximated by atmosphere, clear line of sight without a lot of multipath reflections from the ground, you ought to get something like 30 kilometers range. That's with 10 milliwatts, okay? That's a error-free data stream at that range. So it's an interesting, it ended up being a really interesting design. And it actually all worked, which was just amazing. The white connector up in the corner, a little 4-pin connector, is the other serial port. The 4th pin is so that we've got power, ground, transmit, and receive. That ended up being handy because a lot of the little SparkFun GPS boards have power in it. And as you can see, that's 25 by, that's 2.5 inches by an inch. And then in order to actually have this be useful, we had to be able to receive that as well, right? Because 38.4 kilobit Gaussian frequency shift keying is not something that you could just go to your local ham radio store, if those even still exist anywhere in the world, and buy a device for. So, but hey, we had plenty of these VO.1 circuit boards, and the CC1111 is a transceiver, so it'll receive just fine too. What if I just partially loaded one of those boards, stuck a USB cable in it, Keith cobbled up a slightly different version of the firmware for the board, and all of a sudden we had a new product. Well, we weren't thinking product at that point. This was just how you do the ground station side of the system. And it turns out that worked out great. So for quite a while, what I had was a little plastic box about this big with one of the boards in it, with an SMA connector sticking out of the end. I'd put a quarter wave, whip, SMA whip on the end of the board, and I would use a piece of duct tape to stick that right at the top of the roof of my Chevy Suburban, which I take to launches. And if you've never actually been near a Suburban before, it has this freakishly large, relatively flat roofline, i.e. a big ground plane. And since it was always oriented so the back of the vehicle was towards the flight line, the optimal lobe off of that turned out to be in exactly the right direction. So it's a sleeper, sweet little trick. Just stick it up there, a piece of duct tape, USB cable down to the laptop in the back of the Suburban, and we got a ground station. And it just worked great. So the first flight ever of a board that in a real rocket was in this airframe. That's a 75 millimeter inside diameter airframe. So it's probably, I don't know, 78 or 79 outside diameter. And that flew in April of 2009. A commercial flight computer board flew the rocket because, of course, we didn't trust any of our stuff at all at that point. And where the color changes here, there's a coupler section inside, and that's where the electronics was. So the idea was we're going to light up the motor. It's going to take off at apogee. A pyro charge down here is going to fire that separates the airframe there and just puts the two pieces out on a long piece of Kevlar with a tiny little drogue chute. And then when it gets down closer to ground, a baro sensor indicated altitude will cause another charge to fire up in the front end, blowing the nose cone off and putting out a big parachute so it settles down gently. And, you know, we had good data collection up to apogee, and then everything went away. And when I got the airframe back, and because it did, in fact, recover successfully, when I opened it up, one of the metal mounting screws was just missing. And, you know, the best theory I have is that it came loose and went rattling across the board and shorted something and caused a processor reset. No way to prove that. But we've not yet ever had anything else happen that would cause me to believe that something else was going on that day. Anyway, that was immensely exciting, and we got real data. These are the plots from that flight. And as you can see, here's the motor's acceleration curve, and if you look at sort of if you were to expand, the acceleration during boost, if you look at that plot and you compare it to the manufacturer's test burn data for that particular reload, they overlay really well. In fact, I sent this plot to the motor manufacturer up in Canada, and he came back all excited. He's like, hey, can you do this for some other motors? That did lead to some interesting conversations later, and while I've never flown a motor for free from that manufacturer, I have gotten to fly demo motors from others, and that's been really cool. But anyway, this is all pretty exciting, right? And these plots, by the way, were from the data taken out of the onboard flash part after the flight. But I did actually have successful collection of radio telemetry on the ground during that flight, which is why I knew, I had good data up to apogee, and it's like, oh crap, I'm not getting data anymore. What happened? Fortunately, the flight was to an altitude where the radio direction finding all that wasn't terribly important. We actually watched it through the whole flight and had it back to the ground, and were able to go pick it up. But huge, huge success, but still not perfect. So after getting some experience with the O.1 boards, and we actually flew those quite a bit, with different GPS things attached to them for trying out different GPS receivers. We had some excitement there. One of the first flights we flew with the Surf 3 GPS chip was really interesting because it was in an airframe of Keith's that did not recover anomaly. It actually came back in on a ballistic trajectory. It turns out that when it was coming back down, the GPS receiver hadn't actually figured out what that rapid change in Z was until the airframe was almost back to the ground. And it was really only the last data point or two that we received over the radio link that were anywhere near where the airframe actually was. If I remember correctly, the GPS chip's way of trying to figure out what was happening when it was being kicked in the ass hard vertically was to assume that it was being shoved due west. And so the data, we could talk forever about GPS receivers, but that was just, the behavior of the firmware on the Surf 3 parts was not appropriate for use in rockets. Along the way, we tried some others though. The Skytrack Venus actually worked the best of the ones we tried. And they were available for cheap, and it was a 10 by 10 millimeter, 3 millimeter thick or something, little monolithic thing I could SMT down to, surface mount down to a board. And we were able to buy the chips at first through SparkFun. So we realized at some point that, we really couldn't imagine wanting to fly without GPS in the airframe. So we ought to just put that on the board too. So that's what the version 0.2 is all about. We did a few other things, put some bigger flash, and the board got massively larger. I had to make it another 1/4 inch longer. And this is what that board looked like. The big change actually is you noticed on the previous one I didn't bother showing you the back side of the board. That's because there was nothing there. But what I realized here was that with all the extra parts I needed to stick in to put the GPS in, that putting all of the surface mount parts on one side of the board and putting the through-hole parts in from the other side of the board, which I think I actually have to give Keith credit for thinking that idea up. The consequence of that was that I could still hand load the board at home and reflow it in my electric skillet, and then hand load the parts from the other side of the board, the through-hole parts, and we got the area advantage of, you notice where the big GPS patch antenna is. This is the only impact on this side of the board is where the center pin gets soldered through, and it was a much more efficient use of space. And just to show you around a little bit, that's the CC1111 again with its UHF Ballon filter network. This is the GPS receiver. This is where the patch antenna connection comes through into there. And then this was a connector that I put as a U.FL connector. A lot of GPS modules at that time, a lot of people were using U.FL connectors for connecting the antenna to the receiver. And I don't know why, but I thought it just might be the case that we might want to remote mount a GPS antenna sometimes. Having the connector on the board with a DC bias feed for it and all might be smart. And it turns out that was really important. That's the flash part, the baro sensor, the accelerometer. This is the pyro control circuit down at this end. This is all power supply stuff here. And the USB connector. And again, these boards worked fine. In fact, the first time I ever flew one of these was in Rio Rancho, New Mexico, in a tiny little airframe that was about 32 millimeters in diameter and about yay long. And I put a real kicky motor in it. And we went to launch it, and it was a breezy day. And I'd never flown that particular motor before. And when we lit it off, it was definitely one of those kabam and it's gone kind of events. And it was windy enough that everybody on the flight line was coming by to console me for the loss of my airframe. The fact that nobody had seen it after the motor burned out and all of this. And I was just sort of, shh, leave me alone. I was sitting there watching the tracking data. And I had, the GPS track, and I knew where the airframe, well, at least I knew what the latitude and longitude were. I didn't actually know where that was at that site. But, I was sitting there watching the live data coming in. I knew that the airframe was on its way down and recovery had deployed normally. We just couldn't see it. And it turns out that once it was down, I took the final landing latitude and longitude and put it in my GPS receiver. And sure enough, it was like within 50 meters of the road we had driven in on to get to the launch site. And so I said, excuse me, I'm going to go see if we can pick it up. And we hopped in my Suburban, a friend and I did, and went zipping down, found it, put it in the vehicle, and came back. When it came back so quickly, everybody asked me, oh, did you forget something? Was there something you needed to find your rocket that you didn't take? And I was like, no, we have the rocket. It's probably no big surprise that the club in New Mexico represented about 50% of our first month sales when we finally started. There were problems with this, though. That's a passive GPS patch antenna, and it turns out that for a bunch of reasons I won't go into right now, but because you guys like RF, I'll tell you the big one. That patch assumes that it's on a 50 millimeter square ground plane or larger. That board's 25 millimeters wide. The consequence of that, if you know anything about patch antennas, is that patch is actually several megahertz detuned from where it should be. And so the GPS performance on this board just sucked, by which I mean time to first fix. When you turn the board on, how long it took to figure out where it was really long, on the order of many minutes. And of course, in a development mode, I didn't care. It's like, okay, set the rocket out behind the Suburban and turn it on, let it sit there and warm up and find itself and get a GPS fix. Great, it knows where it is. Now let's go walk it out, put it on a rail and fly it. But certainly it wasn't very satisfying. So the hack was, because that connector was there, I could desolder the passive patch, stick an amplified patch assembly on the other side, wrap the little piece of coax around the edge of the board, slap the U.FL connector on, and lo and behold, the GPS worked brilliantly. So it really was just a question of antenna tuning / gain. But that board ended up being, sort of relabeled as 1.0 and is what we shipped a lot of. This is a close-up of the CC1111 and the UHF end of the board. There are a couple things I thought I'd point out. First of all, the reference designs from TI ChipCon all talked about using 0402 sized surface mount passives for implementing filters. And that's because if you're doing this on either a thin substrate board or a 4-layer board, which is the most likely circumstance, to hit a 50 ohmish trace, you don't want to be a whole lot bigger than the 0402 passives. And so if you try to use larger passives, the whole structure gets bigger. It's much harder to maintain 50 ohms through the various transmission lines, and the filter just doesn't behave as well. Well, the interesting consequence of that recommendation is that all of our boards have used 0402s for all of the passives where we could ever since, because once you learn that you have to deal with parts of that size, you might as well just use them everywhere. Or at least that's the insane approach that I ended up taking. This is the crystal that provides the reference frequency it's 48 megahertz surface mount crystal. And then you'll notice that there's a big solder thing there, and where's the other one? Here it is. No, down here.
No, the two of them, two some parts of town.
Oh, yeah, they're up there, sorry. Those are where the leads, no.
Yeah, they straddle.
Yes, they're symmetrical around the center line of the board. Yeah, you're right, it's those two. Those are where the beeper leads come through from the other side of the board. And you'll notice that these two traces sort of wiggle around that pin. It turns out those are the two sides of the balanced RF coming from the chip. And because it's still balanced there, in order to maintain phase integrity, you'd really like to keep those traces sort of similar in length. So part of the derpiness of the routing geometry there was trying to keep those traces the same length. And there's an inductor and a capacitor in each leg to form the balun, and then the rest of this is mostly just filter. There are a couple of other interesting little tricks. How many of you have ever actually designed an RF board of any kind? Right.
Do they do what? Yeah.
So one of the tricks to making them work is to not put a whole lot of like inductors adjacent to each other, because they'll couple to each other and mutually interfere. Well, it turns out that even in 0402 surface mount parts, this really still matters. And so you'll notice that the little parts that have a greenish tinge, like that one and that one and that one, are inductors. And you notice the orientation of the one in between. I've got two of them like this, and the one in between's like that. It turns out that that's good for 0.3 of a dB, something like that. Likewise, actually this board, there aren't many situations like that, but it turns out that you have to not throw away everything you know about radio design just because you're doing surface mount cute little parts that are all gorgeous little rectangular solids. Those really are, inductors, and they behave like inductors, and they have EM fields around them, and if you line a whole bunch of them up neatly on the board, they will all couple to each other and just work like crap. So the funny thing was, Teledongle VO.2, as I mentioned, so as I mentioned, the Telemetrum O.2 flight generated so much interest, and every time Keith and I would fly things anywhere for the next few months, people would come up to us on the flight line and say, "That's so cool, where did you get that? Where can I buy one?" And we finally decided, actually, at LCA in Wellington in January of 2010, that, okay, maybe we should actually make enough of these to sell a few to our friends. And so the first thing we realized is that the hack of partially loading one of the flight computers to use as a ground station was a cute hack, but if we're actually going to sell them to people, we might do something that was a little more optimized than that. So the first thing we ever produced in volume was Teledongle version 0.2, and it's interesting for a couple of reasons. One is, it's, I think, the only thing that we've built so far that literally worked perfectly the first time. There have been 0 hardware changes to that made from the very first prototype I ever loaded. And
the LEDs are out in the version.
You're right, there's a mechanical change to spread the LEDs so they're a little more visible. Certainly and I did improve the design of the SMA edge launch footprint so that we solder it on the back side too, not just on the front, which is mechanically a lot stronger. But we never actually built any prototypes. We just got a design, we reviewed the heck out of it and went, looks like it ought to work, I think. And we ordered 50 plus of them from an SMT assembler. And when they arrived, we turned them on and they actually worked. It was just amazing. Now, the RF transmitter performance was a little bit limited by the fact that we wanted to keep those cheap, and we did them on a 2-layer circuit board that was, what's the number that you guys use for standard PC board thickness? 1 point? Yeah, right. Which I think of as being 62 thousandths, but yeah, dealing with, you have to understand the weird thing about doing printed circuit boards, and I don't know how many of you have run into this, but in printed circuit board things, a mil doesn't mean a millimeter, it means 1,000th of an inch. And it's such a wonderful unit in so many ways, particularly when you're dealing with centimils and GEDA. But, so anyway, the issue is that you cannot achieve a 50 ohm impedance trace on a board that thick with a ground plane on the back side of the board without making the trace crazy fat. And I'm talking, it ends up being, God, I hate trying to do these conversions in my head with not enough caffeine. The trace width has to be in excess of 1/10 of an inch, so that works out to be, yeah, like 2.5, getting close to 3 millimeters wide. It's too big. So we just give up a little bit of transmitter performance, but guess what? We mostly use these as receivers. We do use them as transmitters, but when we're using it as a transmitter, it's to talk to the airframe when it's on the ground or on the rail, to configure it, to extract data after flight or something like that. And so it just isn't really a huge, big problem. And on receive, that particular impedance issue just isn't quite as acute. So then we released Telemetrum version 1, which was very similar to version 0.2. In fact, I'm not sure we had any significant PC board artwork changes. We just went with the active GPS patch. It's one of those, okay, I'd love to not have to deal with the more expensive amplified antenna assembly, but it works. And people are breathing down our necks wanting to buy stuff from us. So let's just make a few of these and then we'll figure it out and do it better in the future. And we sold of the 1.0 boards, I think by the time I think we only sold, did we do one batch of those or two? So it's like 100 or so of those boards got sold. Then we discovered the approach we were using to reset controlling the processor and the GPS receiver had an issue at certain points in the temperature range, particularly when things got hot, which they can do in the sun on a launch rail at a launch site. So for version 1.1, we added an explicit reset controller. Wanted to be able to measure the ratio of some of the power supplies on the board to try and reduce some noise we were seeing in the flight data. It was cheaper to buy a larger flash memory part by then. And of the 1.1 boards, I think we ended up doing, it might just have been 100, might have been 200. I don't remember. We did a couple of runs of those though. And then along between here and there, the tsunami earthquake thing hit Japan, and the Freescale MEMS facility in Sendai was one of its victims. And Freescale basically couldn't make MEMS sensors for a while. They were fortunately already planning to move all of that to a new facility in Sand Hill, Texas, but they hadn't gotten it done yet. And so the accelerometer that we were using became unobtainium pretty quickly. We, in fact, for the 1.1 production run, I sort of scampered around buying up parts so that we'd have enough to be able to do those. And then by 1.2, we had to pick a different Excel from a different company. We used an Analog Devices part. Worked just great, just cost more, which was annoying. And the interesting thing about 1.2 is I say it was my first perfect RF section. And what I mean by that is that on all of the previous versions of Telemetrum, the TI ChipCon specs for the transmitter performance were approximately being achieved. And what I mean by that is they said that we ought to be able to get plus 10 dBm of transmit output power, or 10 milliwatts. And I'd see anywhere from 9.3 to 10.2 or something like that. And that felt close enough to 10 that, yeah, okay, that's fine. On a version 1.2, I never ever saw a board with less than 10.1. They were all somewhere between 10 and 10.5, plus 10 to plus 10.5 dBm output. So that's the one where I finally got the filter design, the layout, and the component selection right to actually achieve what that chip's capable of. And we really like that design. The only changes on 1.2b, which between these two we sold 300 boards or something. And 1.2b we'd sold a few of before the rest of them burned up. The only changes in that were little mechanical improvements, that better SMA footprint, for example. In any case, all of these things and some other products we did were all based on the CC1111. But then stuff changed. I got this crazy idea that it would be nice to do a flight computer for supporting more complex flights. And in the rocketry world, that means instead of just a pyro event at apogee and another one coming down to put out the main parachute, wouldn't it be cool to be able to air start additional motors or support multiple staging, and so forth? And another thing that was happening is that people were starting to recognize that if you're flying complex flights, being able to not fire extra motors or do the second stage ignition if something had gone wrong previously was a good idea. What do I mean? Let's imagine you have a two-stage rocket and as it's taking off, the motor in the first stage has some kind of a problem, and instead of going up vertically, it kind of lays over sideways and then starts burning, and you've got a lot of horizontal velocity. Let's say further that it's kind of aimed towards the spectating crowd. Is this a good time to light the second stage motor or not? I love you guys. A number of you going yes. It's just awesome. So actually, a guy in the US came up with an interesting idea. He spent quite a bit of time actually analyzing sensors. It's all written up in Rockets magazine over the course of several issues. And in the end, he basically did an inertial management unit design to figure out which way the rocket's oriented. You know, is it still going mostly vertical, or has it laid over for some reason? And what he designed was a board that could go between your flight computer and the pyro charges to sort of provide an extra degree of gating on whether to fire the charge or not. So it basically provided a pyro event inhibit if you were too far away from vertical. And it was called the tiltometer. Kind of a cute idea, but I looked at it and went, oh my God, that board is several times as large as my entire flight computer, and he only handles one channel, and ... So I asked Keith, I said, so how hard would it be if I put some more sensors on the board for us to actually do this all just, you know, on our board? And I think his answer was, not with an 8051. So we ended up needing more processing power. We ended up picking an ST Micro's Cortex M3, which is a pretty gutsy ARM implementation. We're running it at 32 megahertz. You know, it's full 32-bit processor, GCC for code generation, ... And the only problem is, that's a cute processor, but it doesn't have a radio. Fortunately, our friends at TI had come out with a next generation of radio devices. And the only ones that they made that had a built-in processor had strange things like they didn't include USB, and the processor really wasn't enough gutsier than what we'd had before to be interesting. So the part we ended up focusing on is the CC1120. It's another sub 1 gigahertz radio chip. In this case, it's meant to be a radio peripheral, not a full RF system on chip. And it's got higher transmit power and a much more sensitive receiver. Our theory is that the way they got the receiver sensitivity was by taking all the cool digital stuff off the die, because it no longer included the decoder, the hardware decoder for the forward error correction scheme that we were using. As I say, much fun for Keith. He would prefer that I say much more fun for Keith, but it uses a slightly more complex filter design. We end up using 2 crystals because The ST part wants one crystal frequency to make USB work right, and that's not an easy one to also use for the radio. And we ended up using that for the new board. And then Telemetrum version 2 is basically a subset of the Telemega design. So it's the same features as Telemetrum, but all the specs are a lot better. A couple of other things that I thought I'd tell you about just briefly, and then I'll shut up and let Keith talk. As you notice, we have GPS receivers and UHF transmitters very close to each other on the same board. And it turns out that with the SkyTrack parts, this wasn't a huge problem because we were using an amplified patch antenna. The amplified patch, the more recent ones we were buying, actually had a SAW filter built in, so they were really only amplifying a narrow range of frequencies around the GPS L1 carrier. And we're doing a pretty good job of knocking down interference. However, when we switch to the U-Blox chips, which have much better high dynamic performance for use in rockets, and are very sensitive so that I actually can go back to using passive antennas with them, the problem was that now all of a sudden I've got a hypersensitive GPS receiver with a passive patch and nobody else providing any filtering, sitting right next to a relatively strong source of 435 megahertz. Shockingly, that didn't work so well. And in fact, Keith confirmed this by just tweaking the firmware to turn the radio transmitter off, and all of a sudden GPS would lock up quickly and give us great results. And anytime GPS, or the UHF transmitted, GPS kind of went, whoa, what just happened? It turns out, fortunately, there's a good fix for this. Tiny SAW filters, which is, it's a surface acoustic wave filter, little passive part, are surprisingly available and cheap because everybody's cell phone has one of these on the GPS receiver. And as a consequence, our Telemega GPS performance is really outstanding. That part, by the way, is that one. So just to give you a sense, let me blow this up. This is the RF section. So just so you can see, this is the CC1120. That's its crystal up there. It has a somewhat more complex filter and balun design. You'll notice that in this case, the balun, I've got sort of nice trace uniformity out to here. It goes through the balun, and then this is all filtering down through here. Lots of bypass caps and all. This is where the GPS patches pin is, and right there is 40 milliwatts of UHF. So, and distance-wise, that's that far apart. So that little part right there is the magic secret sauce. That little SAW filter makes all the difference. It allows that GPS receiver to not hear the UHF transmitter, and we get excellent GPS performance. But once again, you'll notice that here's another pair of inductors that are very carefully mounted orthogonally to each other. There's another pair there. It's interesting. Some of this ends up being almost art when you're sitting there in the CAD system trying to sort of get these things right. It's unfortunately just time consuming and expensive enough running cycles that you don't try as many things as you'd really like. And then finally, most of our products use transceivers, but we've thought sometimes about things where it would make sense to do transmit-only products, and TI makes some parts there. There's one we really like called the CC115L. It's the L are their new low-cost value line products. This one has a relatively simple balun and filter requirement. We're actually going to use this on an upcoming product. This one makes up to plus 12 dBm, so it's a little bit more than the CC1111, but not in the same range as the 1120. And these are really cheap parts. The 115L is less than $2 a piece at quantity 100. I mean, it's sort of impressive what this stuff's doing. For higher power, we generally believe that it's a whole lot better to use more receiving antenna than to try and put more transmit power in the airframe. It just simplifies things a lot. But we've played with higher power transmitters. RF Micro Devices make some parts. This one is particularly cool. That one's good for about 1/2 watt. And it wants plus 10 dBm as its input, so it's very compatible with either the CC1111 or the CC115L, which can be programmed to put out sort of whatever power level you want. Keith initiated and he and I collaborated on the design of a GPS and radio transmitter only product. And we did a version of it that used this. We built 3 prototypes. One of them worked perfectly, and the other 2 had issues we never got resolved before those boards unfortunately disappeared. We may do some more with this someday, but frankly, in the rocketry world, it's not clearly wind, so we haven't played with this a whole lot more. I won't bore you with the business stuff. It's kind of cool, though, that the fact that something we started at LCA in Wellington has helped us turn our hobby into a completely successful 100% open source business. All the design tools we use for everything we build, hardware and software, all of the software that we're using for finance management and for the web store, and everything's 100% open source. When I say 100% open source, I mean even for all the hardware designs and everything, they're all up in our Git repository and they're all licensed under open licenses, so feel free to go take a look and learn about it. I'll be talking on Thursday afternoon about the events of June of 2013. But if you're interested, altusmetrum.org is where to learn a lot more about all of this stuff, hardware and software. With that, I'll stop. Thank you for your time and attention, and we'll turn over to Keith. I might suggest if anybody has an immediate question, that would be fine, but maybe we hold most of them until later.
The RF design, did you just base it all on the TI upload, or did you do it with customers charts or the screen software?
The schematic level implementation of the filter designs and balun designs that I'm using are from TI app notes and design recommendations.
The routing for the circuit board.
That's all. I just lean back, get into the right mental state, and start laying parts down. No, I'm not following TI's recommended designs at all, and I'm not using fancy tools for doing serious analysis of the designs.
You gotta remember, it's only 400 megahertz.
Yeah.
Basically DC.
Yeah. So Keith has adopted these attitudes from hanging out with me for a while. I mean, I hold some microwave distance records and things, so I'm not being facetious when I say that at 400 megahertz it's not that challenging. What's challenging about it is trying to make these things completely repeatable. It's one thing as a ham to sit at the bench and put a bunch of parts together and hook up your test equipment and kind of tweak on it until you get the performance you want, and then go, rah, let's go roving in the contest and make a bunch of contacts. It's a different thing. You have to do that's 90% of the job. You have to do the other 90% of the job if you want to make something that's repeatable that you can actually just sell to other people and they'll go plug it into their, screw them down in their rockets, hook a battery up, go fly them and have good experiences. And that's where a lot of the time gets spent, is obsessing over the details of, we ought to pull those passives a little farther away from the mounting screw in the corner because somebody's going to whack them off the board with using a screwdriver that's too big, or, that's happened. And it's stuff like that so there's not a single place where I've actually ever copied a TI ChipCon artwork reference design. I always look at them. I always sort of lean back and stare at them, and I wonder what that intern was on when he designed that. And I mean, look, I worked at HP long enough. I know exactly where app notes and ref designs come from. They're the things you give interns to work on, and somebody provides advice and guidance. And in the end, they all get blessed before they get put out. But yeah, whatever. Okay, Keith?
Thanks for that.
Sure.